Absolutely. If we actually find your IETF. So it's. Have you ever talked to me? No.
No, we did the set servers.
Others?
All right, so I guess we should get started. So this is the Rmcat working group. I'm Colin Perkins. I'm one of the co-chairs. We have Anna, hopefully one of the other co-chairs on Meet Echo, and Chaching as well, who will be giving one of the remote presentations.
Click on that mirroring tool. Click on what? See where it says mirroring to Midra? If you click on it, it'll go.
Okay. There we go. You expect me to be able to work the Chromebooks, huh? Can you hear me, Anna, Chaching?
Yes, we hear you, or I do at least.
Okay, excellent. Chaching, are you there?
Yes, very well. I forgot to activate my mic.
Okay, good. It seems this is all working. All right, so let's get started. So as I say, this is the RTP Media Congestion Avoidance Techniques Working Group. We have the usual note well. Hopefully everyone is familiar with this by now. You have to disclose IPR, and we have a code of conduct and the like. Today's slides are all in the data tracker if you want to follow along. We have Mute Echo. Is anyone in the Jabber room in the room, Jonathan? Okay, if you can keep an eye out for comments in there. If I forget to press the red button, someone shout at me and I will enable the remote participation. I will attempt to take notes. If anyone else could take notes, that would be helpful, and then we can combine them to make the minutes. If you can take notes, please send them to me. So we've got a reasonably light agenda today. We've got this introduction and status update to start with. Then Xiaoqing will give an update on the NADA implementation and some new evaluation results. And then we'll finish up. I have a very brief presentation about the congestion control feedback draft, which will mostly be discussed in AVT Core on, I think, Friday. So looking at the document status, we have a bunch of congestion control algorithm candidates and related documents. The Google congestion control draft has been dormant for some time, and I'm not expecting that to be updated, although we would be open to an update if the authors care about that. All of the other drafts, the NADA algorithm, SCREAM, the shared bottleneck detection, and the coupled congestion control are either in the RFC editor queue or have been published as RFCs already. The requirements draft, the congestion control requirements, has been in the RFC editor queue for a very, very long time. I believe that's part of cluster 238, so hopefully will appear before too long. The evaluation drafts, the video traffic model was published reasonably recently. The eval test draft has been approved and is with the RFC editor. And the eval criteria and the wireless tests went to the IESG since the last meeting and are waiting for processing. The congestion control feedback message, I'll give you a brief update about that later today, and it will be discussed in AVT Core on Friday. My belief is that this is now ready for working group last call in AVT Core, and hopefully we will be able to wrap that up pretty quickly. The Rmcat congestion control feedback draft had a very brief update prior to this meeting, which just fixed a bug I noticed to make the calculations actually match the description in the text. It turns out that you have to specify the dependencies in the make file if you want things to be updated correctly. For that draft, once the feedback message has been finalized, that will then get revised with the accurate numbers. And the congestion control framework and codec interactions drafts have both expired, and we will, I think we previously decided that we'd reconsider those once the candidates had gone to standards track, and that may be some time. So these are basically dormant. We have a number of milestones. I have omitted the milestones that have been done for some time on this draft. The others, we had a milestone for December 2018, which was to submit the requirements and evaluation criteria drafts to the IESG. We're almost a year late, but we managed it within a year after the deadline, so I consider that a great success, and we have succeeded in submitting those to the IESG.
A lot better than WebRTC.
A lot better than WebRTC, yes. Yeah, it's a lot. Yeah, the milestone's been delayed a little, yes. The evaluation results were supposed to go to the ISG in July. We're supposed to publish a first draft of the standards track congestion control in July, and we're supposed to submit the final version of congestion control and the interactions to the ISG by this meeting. I think it's reasonably likely that those are not going to happen. Especially the ones in the past. So the suggestion from the chairs after a little bit of discussion was that we would spend the next 12 months or so gathering evaluation results and implementation experience and practical experience using some of these algorithms for the next 12 months or so. And keep the working group alive, and if there's things to report, then we can have meetings and have some reports and some discussion. And if there isn't anything to report for a particular meeting, then we can not meet at that time. And then in a year or so, we can evaluate the status, see where things are, and see if we should continue and pursue further work, and see if there's any interest in taking any of these to standards check. I don't know if there are any opinions on that from the rest of the group.
Jahid, yeah, I think that sounds good to me. But what I was wondering, like, what do you do with gathering evaluation results? How do you gather it? Like, is it like, I mean, we have been showing results when we were developing the condition control algorithms. You have a quite amount of evaluation results there. So basically, what exactly we would like to gather that was not already there, and how you would like to gather that? So where do we have the discussion?
Well, I think we should have that discussion in this room. Yeah.
Mia Kulevin. So what we usually do for congestion control, not that we have like a bunch of congestion control schemes standardized in the IETF, but like we've been carefully about standardizing them at proposed standard because we want to make sure it's safe to use them on the internet. So I think the only way to figure out it's safe to use them on the internet is to actually use them on the internet. So what you want is deployment. You want not only evaluation results, you actually want like live results of deployed traces and whatever. If you can't get that, then maybe we shouldn't go for proposed standard, which I don't think is like a bad thing, because you can use congestion control without like having interoperability problems or whatever. It doesn't really matter if it's experimental or proposed standard. So, but like that would be my bar.
So Jahid again. So do we have an expectation of like what is the spread of the deployment? Like this amount of traffic need to use some condition control or something like that, or how? I mean, deployment, yeah, of course. Like what we can do, we can what exactly for Scream we did. Basically, we have it open source. We have a couple of cases that we used it in different trials and tests on the live network. And also we know like some people are working on it. It is on GStreamer and stuff like that. But if you want me to collect all the like instances of using Scream, it will be very hard for me to come and get an answer. So what I would like to rely on, like anybody using those NADA, Scream, or GCC, come and show up here. And that's also like an not really realistic as on my expectation, I would say. So what do we do here? I mean, that's my question, basically.
I mean,
for 1 year, I mean, we said like 1 year we're gonna gather evaluation results and experience, but
I mean, you know, this as a group, I don't think we can force people to use these, right? If people are using them, if people are doing experiments with them, we would appreciate feedback. If people are not, then okay, maybe we just leave them as experimental. Cha-ching? Do I need to push the button?
Yeah, hi. Actually, I meant to ask about it after my presentation, but I think since we're talking about the plan for the working group, I might as well mention. I have sort of similar maybe question as Zahid in sense of for the evaluation stage, we're no longer talking about evaluating the performance, right? For that, we have the test case, we have all the collection of some preliminary set of results. Now that we're talking about trying to gather deployment results, I was wondering whether that's a good expectation, but I was wondering whether there's any sort of more concrete guidelines around it. For instance, the question I wanted to ask after my presentation was that we basically put in the implementation as kind of a experimental branch, if you like, as the browser, and built-in an alternative method inside WebRTC. I was kind of curious to know whether any of the owners of either WebRTC modular or inside Firefox is interested in trying it out on a larger scale. So maybe those type of things. So maybe this is more a call for participation, either inside this working group, and I guess we can also reach out to people who are potentially interested. Yeah, but then, so that's my comment in maybe trying to encourage evaluation of this method. The question is, do we also have guidelines? Let's say if someone is interested in contributing to large-scale evaluation, what do we tell them? What type of stats to collect? What type of, how to run comparison, things like that. Thank you.
Okay. I think we have all the various evaluation drafts, which list the type of things we look to evaluate. Now, obviously, what you can do in a simulation testbed is not the same as what you can do in a real deployment, but metrics along those lines, just general experience. We have used it, or we have seen other people using it. It doesn't seem to break anything. Just some general experiences from people actually trying it out and seeing if it really works.
Yeah, Mia Kulevin, let me add one point. So we also discussed that, or like we decided a long time ago that we don't need like to pick one that is the winner, right? We can document all of them, and then we see what deployment, which deployment will happen. And so I think at this point, it's also not about comparison anymore. It's not to say this one is better than the other one. It's just like, if you can prove that there has been deployment and it didn't melt the internet, then we can move to standards track. If not, it's fine as well. I don't think it's a problem. So like, I really like the plan, having the group open for 12 months, see if there's like anybody who can report on these things in this time frame, and then if so, we can move ahead. That would be great. If not, I don't think it would be failure for this working group. It would be fine as well.
Hi, this is Nitin from Facebook. I just want to add that we did some experiments and some deployments of one of these algorithms in a different use case. And I would love to, like my team would love to present at one of these working group meetings maybe next year.
Great, that would be really helpful. Yeah, thank you.
Jonathan Lennox, I think I mentioned on the mailing list that I'm working for the Jitsi open source conferencing project now, and I think I mentioned on the mailing list I'd be interested in trying out various algorithms in our open source SFU. We could certainly even try various algorithms in production. I mean, the thing about an SFU obviously is your subject. You can only send what the browsers give you, and getting which basically means GCC because they're all Chrome. But we can certainly, that's something that we'd be open to contributions to try out various algorithms in our code, even potentially in production.
Okay, thank you.
Yeah, I think I agree with Maria. Like, I mean, it's fine with if we have the results, we have a standard. If we don't have results, we have experiment. And I think we have now somebody saying here, like, yeah, they're doing experiment, and hopefully they're doing more than like GCC, right. Because I don't think like GCC is experimental right now.
GCC is an expired internet draft right now.
That's expired internet draft, but it is got deployed. So basically, if you guys are coming up here and saying like we have evaluated GCC, I mean, that actually doesn't help us, perhaps. So so my expectation, like, you will do more than GCC.
So I just want to add that like at the time when I submit the proposal, like maybe to the chair, like you can decide whether it's worthwhile or not. But like our work is not just purely evaluating GCC. Like we actually applied it over a quick instead of UDP, and we applied it we applied it to a different use case than video calling. So there might be some interesting learnings for the group. Like I can submit a proposal and then we can decide.
Yeah, I mean, I think that would be interesting, and we'll see whether this group is the right place to do it, or whether we should possibly point you at the congestion control research group. But yeah, it sounds like interesting work, and it would be useful to hear it presented at least somewhere in one of these meetings. Okay, so how I'm reading that is that there is general agreement that this is a reasonable approach, and we will have to see how things go with the evaluation. It is clearly difficult to be prescriptive. We're not going to say you need so many 100 million users and minutes of deployment experience, but if people are using it and getting some experiences, then please report back. Okay, so the only other thing I think I think that's the last of these chair slides. I mean, obviously, once we're talking about implementation experience, we had a hackathon earlier this week. Did anyone play with the Rmcat algorithms in the hackathon?
Jonathan, so I mean, the main thing I worked on in the hackathon is to try to get more visibility into tracing and debugging of what the algorithms are doing, because it's very hard to say, okay, what actually happened here? Is the fact that my bandwidth just dropped, some weird quirk of my algorithm, or really effective of my network? So there were Sergio, I think so, developed a bunch of visualization tools, and so we're working on getting a common input format that our congestion algorithms can output, such that we can feed these visualization tools to figure out what actually happened, which is a very important thing for an actual production system. The other feedback we had, more about not so much what we did, but what we complained about not having, was one thing that would be useful to us is have a practical way to turn like some of the guidance in the test cases into, for instance, actual commands we can type into Linux to turn on the various traffic shaping algorithms to say, okay, let's make something that looks like, so we can actually test on our real systems what's actually happening. And there's these various tools. There's this tool TC in Linux, which is nearly incomprehensible to mere mortals. There are various front ends to it, but it's always not clear whether the front ends are doing what something realistic, because it's very easy to get to pick the wrong traffic class or traffic shaping and get something that's completely unrealistic compared to what the test cases are trying to do. Particularly for things like the wireless test cases, we have no idea how to make something look like a wireless base station using TC on Linux. That is extremely non-obvious.
Yes, that's not simple.
So if anybody has knowledge or knows somebody who has knowledge who can sort of help turn this into something more practically realizable, especially as you get a lot of weird cases, like when you change the settings, have it not do something completely off the wall and like throw away all the packets that were in the queue when you change the settings or something like that, which usually causes congestion algorithms to go completely haywire.
Yes. That's possibly something that it might be worth asking the MapRG list, because that maybe some of the students who've been doing evaluations and testing for some of the things there might have some experience.
Yeah. The other thing we found is that a lot of both the algorithms and the test cases are written from the point of view of endpoints, whereas the things that the people who are working on it are actually working on are SFUs. And so I think we need to, sometimes you get things like where the algorithms will say, okay, when this happens, tell the encoder to send more. And well, I can't do that. I'm an SFU. So I think sort of more, clarity somewhere on, how an SFU should behave and how an SFU should be tested would be helpful to us.
Okay, thank you. All right, anything else before we move on? No? Okay. So next up is Cha-Ching, I believe. Okay, Cha-Ching, that should be your slides up. I don't know if you can see them.
Yes, I can see it well. Just checking if the room can hear my audio going through fine.
Yes, very clearly.
Okay, great. Yeah, so this will be an update on the NADA evaluation results following the most recent version of the draft, and also somewhat updated implementation in the open source Firefox browser. Next slide, please. In terms of the draft, the main update is really a recent sort of back-to-back two version updates to address comments from both the Gen Art and the Direct, I don't know, last call reviews, as well as the telechat reviews. Basically, right now the draft is in the editor's queue, and most of the changes to the draft are mostly editorial in the sense of trying to either be more inclusive or trying to revise these discussions for more clarity. And there's no algorithmic changes for the draft. And also the details of the revisions were summarized on the mailing list when we haven't version updates. So folks are, feel free to check them out. And I think usually the diff view also gives very quick and concise comparisons of revision updates. Next one, please. And implementation-wise, compared to the last round of presentation, we have updated our implementation to now include all the full-blown algorithm features, and in this updated version of the implementation, that includes the mapping, the nonlinear delay warping mapping to the congestion signal, as well as incorporating loss as part of the congestion signal penalties. So this way, the evaluation results I showed today do reflect all the features. That's kind of the bells and whistles that's in the draft. And the other things are mostly for inconvenience. We basically added similar logging mechanisms to the default rate adaptation modular and inside the WebRTC modular. So this way, basically, when we do comparison, we can have similar logging for comparison of stats. And we also enabled, my colleague Sergio, he worked on enabling on-the-fly switching between either running the rate adaptation in NADA or in the default mode using the browser, sort of a config panel. So that just sort of made our evaluation effort a bit easier instead of having to recompile different versions of the same code. And then I provided a link on kind of the current version of the code. This is basically a branch that I forked off the WebRTC, Firefox entire browser code, and we added both the NADA rate adaptation modular there. We actually have two versions. We have both the round trip based version, which is somewhat more like a fallback if you don't have the updated version of the transport feedback, or the one-way delay based NADA, which reflects better all the features in the draft. And it's the code. People feel free to check out the code, sort of take a look at the code too. Next slide, please. So in terms of evaluation results, in this round, we basically took the feedback we gathered from our previous presentation, in the sense that previously when we presented results, we'll always have bidirectional calls and always compared the forward direction versus the reverse direction, because the senders were running different algorithms, NADA versus Chrome, and people were having some concerns about they don't necessarily follow the same path. So the results I'm presenting today, although we still set up bidirectional calls, and all the performance metrics, basically all the monitoring logs come from the direction from client A to B, and we switch back and forth between the default behavior versus the NADA-based rate adaptation. And as mentioned before, for convenience, we both added logging on the sender side to gather feedback from the receiver, as well as per packet feedback information, which is embedded in this kind of this updated new form of a transport, which Chrome already supports. And the other maybe side note is that for NADA, the algorithm, we do impose both a max and minimum rate for the rate adaptation, whereas per my observation, I haven't observed a clear rate boundary for the default algorithm, and we set the default resolution to 720p. So with that, and then on the side, since we do gather all the logging information on the sender using our own code, we also try to corroborate that information by taking screenshots on the receiver, because Chrome, the WebRTC internals tab, do provide you with figures of various metrics of interest. So with that, we can probably now start taking a look at some of the evaluation results.
Question?
Yes, please.
You modified Firefox to support Transport CC, because I know by default it does not.
And that's right. That was, I believe that's the fruit of one hackathon, maybe a few meetings away. It was mostly work from another co-author, Sergio Mena. He's, due to time zone difference, he's not attending the meeting today. He was mostly working with Neil from Mozilla, if I remember correctly. So they do have, basically they enabled Transport CC inside the Firefox. Yeah, okay. So we're building upon that. Yeah.
Okay, thank you.
And Chrome already supports it, so it works well for us. Yeah. The other thing I want to call out is that this type of feedback, the default interval seems to be at 50 milliseconds, once 50 milliseconds, we do get a feedback, and the feedback information embeds per packet acknowledgement, information. So that's we basically have all the information we need for running the NADA algorithm. Great, so we can move on. Next slide. I just want to mention, as I mentioned before, now we're focusing the comparison along one direction. So at least hopefully, between the same sender and receiver, they follow the same path. We still can't really do idealized comparison. So what we do is we try two different mechanisms. One is back-to-back sessions. So basically we run one call using the default, immediately followed by another call of similar duration using NADA. The other thing we do is that we also try a little bit about running two parallel sessions between the sender and the receiver, one of them running NADA, the other one running default. So this way, at least we subject them to the same path and any loss and delay pattern. And we also get to observe a little bit about how NADA competes against another default WebRTC call. So in terms of evaluation scenarios, I'll be presenting two different settings. In one setting, it is a call between, I'm based here in Austin, Texas. So the sender is based in Austin, Texas, and the receiver is based in California. So it's a kind of a cross-continental or within the US, sort of domestic long distance call. The other one is between Austin and Europe, basically between my side and my colleague Sergio based in, he was taking those calls from Spain, so that you guys would see that it would involve a somewhat longer round trip delay, baseline round trip delay for the path. So these are the two settings. For each of the settings, we try both the back-to-back session and parallel. So we're looking at 4 sets of comparison results, if you like. We can move on to the next slide. So this one for back-to-back, I thought it would be easier. So even though we do default first followed by NADA, I thought it would be easier to show both of them side by side for ease of comparison. So we have both the rate, the delay, and the packet loss ratio. For the rate, the blue lines show the target rate calculated by the rate adaptation algorithm, whereas the red dots are the kind of the measured acknowledged rate based on the per packet feedback information. And the red rate are calculated using a interval of 200 milliseconds. So they're somewhat noisier compared to the calculation of the target rate. The middle two graphs show the round trip delay, round trip time in red, and the queuing delay, which is kind of derived from within the algorithm by subtracting out the long-term baseline one-way delay is in blue. And the final two graphs show the instantaneous packet loss rates. Basically, we take the packet loss rate within a window of, the 50 millisecond feedback, look at the gap in any sequence number, and also try to do a temporal smoothing. But still, we do see that even though losses don't occur all the time, when they do occur, they can be quite spiky. So these are the 3 sets of metrics that we keep track of. Maybe the main observation, and here in the bottom, I list out the kind of the baseline RTT we observe, which is the minimum RTT over the path, which is around 60 milliseconds between Austin and California. And the maximum RTT we observe is around 2.2 seconds. So when things do queue up, apparently some of our routers along the way have deep queues. Yeah. So with that, maybe the main observation I want to call out on this slide is that obviously they are back to back, so we don't really have a exact comparison, but maybe qualitatively we still see the amount of losses they experience are similar. They experience sporadic and sort of hiccups over the network. The default algorithm seems to be a little bit more so when they back off and take and ramp up again, it takes a bit longer time, and they actually incur sort of a little bit less and delay, so somewhat less aggressive. Whereas the NADA core, what we do notice is that it's very fast to ramp up, and whenever there's a hiccup, it recovers from the hiccup quite fast. And so, and interestingly, even though these 2 cores are between 2 sort of enterprise offices, it turns out the Wi-Fi situation can be quite noisy and busy between both offices. Yeah. So next one, please. So this is from the same experiment. I'm just showing the screenshots captured from Chrome browser for each of the sessions, more as a corroboration. I guess qualitatively, the kind of both the rate profile as well as the frame per second do reflect the rate we have measured internally at the center. So these are really more corroboration plots to make sure that our logging mechanism is not broken. Yeah. Next one. So under the same setting, we now have 2 cores side by side, and both the default and NIDA, they actually share the path and over the same time. That's why if you take a look at both the delay and the packet loss ratio, we do see very synchronized behavior, which is not surprising at all. And again, occasional delay spikes in this one. So in this one, I guess the red dots of the NADA core in terms of how much rate actually gets through is a little bit hidden behind the blue busy lines, but it's sort of mostly, there's one big dip between 0 and 100 seconds, but after that, it most of the time it sustains quite well, whereas the default core took a bit longer to gain a sort of a greater share of the bandwidth. It also does not seem to be a case where the bandwidth is fully limited, because both of the cores are operating more or less at the maximum sort of available bit rate of 2.5 megabit per second, for instance, during 300 and 400 during that period. Yeah. Next slide, please.
Yeah, Churching, it's a little hard.
Yes, go ahead.
The red dots underneath the blue, is the red line stable for NADA?
It is mostly stable after, I would say, after 100 seconds. So there was a big dip between 0 and 100 seconds. We can see a little bit from, yeah, sort of seeing through the blue screen a little bit. Yeah. After that, it's quite stable. We can also see those rate profiles in the next slide, reported by Chrome.
Yeah. Okay.
Yes.
Great.
Yeah. One thing I'm not sure is what's the kind of the measurement interval of these bytes received per. By the way, everything is bytes received, so all the numbers would need to be multiplied by 8 to corroborate with the numbers in the previous page. Yeah, I'm not too sure about at what time interval they sort of measure rate. Yeah, but other than that, both the rate and the resolution and the frame rate do sort of correspond to what we observed in the center side in terms of the acknowledged received rate. Next slide. So for this round of, I thought it would be also interesting to, since we're mostly interested in reducing latency or at least confining latency for a conferencing course. So what I did is I basically plotted out the CDF of the queuing delay from each of the sessions and put them sort of side by side for both the back-to-back session and the parallel session to form a comparison. I called out some numbers here, but I think maybe the main observation for this round is that there's not really a main advantage of the NADA scheme with respect to the default. In fact, for the back-to-back session, since it was a little bit more aggressive, it actually, sort of the CDF is somewhat worse compared to the red curve. But that said, we can also see that if you take a look at 95th percentile of queuing delay, we can limit it below 100 milliseconds for sure. And I guess that's a good news, both for the default algorithm as well as for NADA. So next we can move on to the cross-Atlantic calls. So first one is back-to-back calls. So again, this is maybe as a reminder, this is between Austin, Texas and Valencia in Spain. And here, in general, for this round of experiments, we observe a little bit less interruption, sort of hiccups over the network. Ironically, this set of results I was sending from my home using Wi-Fi and then backed off by Google Fiber. So it might be quieter compared to an enterprise environment. So with that, we see the similar behavior as we can see before for the default algorithm, where if it does experience a delay spike, then it will take a, sort of on the order of tens of seconds to ramp up. Whereas in NADA, even though it is subject to similar types of delay spikes, the ramp up back is much faster because of the accelerated ramp up feature in the rate adaptation algorithm. The other thing you might notice is that there's a kind of a floor of the round trip time around 190 milliseconds. So then, all the red curves are kind of floating above the blue ones for this set of results. And for plotting purposes, all the delay graphs are kept at 600, but as reported below, some of the spikes actually reach as high as 4.5 seconds in terms of round trip time. Next one. So similar Chrome screenshots to corroborate our observations. Yeah. Interestingly, for this round, even though we see, okay, I'm not too sure the screenshot for the default behavior, because it seems to be a little bit different from basically the previous. Well, no, I think it's fine. So basically we have two dips in the default algorithm, and then I guess this screenshot missed the second ramp up duration for that one. For the second ramp up, so it's not qualitatively corresponding as well. Next one. Now, so this is in parallel, the default comparing against, sort of competing against NADA in parallel. So again, we can see that both the delay and the packet loss observations from both of the floors are very comparable. And for the default algorithm, even though the target rate can sometimes ramp up very high and go back and forth, the actual received rate is quite stable. Whereas for NADA, we see very similar behavior as before. And next slide is for the Chrome observation. There was one figure that we forgot to capture, so I no longer have the bit rate. But other than that, we see, for instance, the Chrome reported bit rate for the default algorithm. One thing to note is that it is actually kind of below. Basically, typically the max rate is at 300K bytes per second. So this one the receive rate for default algorithm is quite stable, but stays somewhat lower than its full potential. And the NADA graph, we don't have the rates figure, but judging from the frame rate and height, we see that there was one sort of a dip in kind of the beginning part of the call, and for the rest, it was quite stable. Next slide shows the comparison of the queuing delay. So for this round, for both of the back-to-back session and the parallel sessions, we do see an improvement in terms of the queuing delay distribution of NADA with respect to the default algorithm. I suspect part of it is sort of attributed to the kind of the big spikes and then the low ramp-up time. And so overall, if we look at kind of the percentile numbers for the blue NADA stream, it's also quite good. It's actually interestingly for this cross-Atlantic core, if we're looking at queuing delay, just because the sender side is in a less noisy wireless environment, this performance is actually better than the previous one. So it's not really dominated by the pass RTT. We're mostly measuring queuing delay here. I think that's the end of my observation slide. So in summary, I think maybe some of the consistent observations is that the proposed NADA algorithm do have a fast initial ramp up to achieve the maximum allowed rate, and typically that's within a few seconds, whereas the default algorithm, if it does go down, it can take on the order of tens of seconds, and it can recover, and the proposed NADA algorithm can recover quickly from temporary losses and queuing delay spikes. It seems to be quite robust to hiccups in the network, and it can effectively limit the queuing delay buildup. I wanted to put in some numbers, like 90th percentile queuing delay is below 100 milliseconds. And it does not really starve the competing WebRTC flows. So when we put both of them side by side, so at least, I'm not too sure. I think the environment we test is probably not a bandwidth limited environment, given that both my home Wi-Fi connection is quite sufficient and obviously enterprise network, it can be busy, but it's probably not bandwidth limiting. So in those environments, we don't really starve a competing call. So that's probably relatively safe to Mira's early point or concern about how it works against existing traffic over the internet. And for further investigations, the main things of interest would probably to try it out over bandwidth limited connections. There was some suggestion about trying it out over LTE links that we haven't got a chance to fully investigate on. And we're also interested in understanding kind of coexistence of if we have multiple cars running our algorithm, how it works. That's something we'll be able to get evaluation results on even using our existing setup. And the other thing of interest would be to try it out with running some kind of a TCP-like background, long-lasting file transfer type of traffic. So that's kind of the update I have for this meeting for the NADA algorithm, both in terms of evaluation and some additional ideas. I'm also here to maybe gather further feedback and suggestions. Thank you.
Okay, thank you. Any questions for Jiaqing?
So what are the plans for trying this out in real production traffic?
Sorry, yeah, so that was the question I asked in the very beginning. Frankly speaking, we currently don't have any, we haven't laid out a plan to try it out in a large-scale deployment yet. That's something obviously we would be very interested in gather results on, but also like these are the type of tests I run with my colleagues kind of manually, and I find them to be always surprisingly taking longer than, a little bit awkward. Yeah, so that's another thing we're very much interested in. Yeah, either like learning from maybe folks like you guys in understanding how to set it up, or maybe collaborating with people. Yeah, so I'm quite open to suggestions too. Yeah, so
my other question is in slide 11, if you can go back to that. I noticed that on the top left side in the default case, the acknowledged rate is way higher as compared to the target rate. Do you know why that is?
Oh, no, I think you, so the blue curve is the target rate. The red dots are the acknowledge rate. We basically measure based on per packet feedback and average kind of the size and interval. Yeah.
Labels are incorrect here, so it threw me off.
Oh, okay. Sorry about it. Yeah. Okay. Yeah, I think I changed color later on. Yeah.
This is Ayush from NUS. Have you tried evaluating different combinations of default and NADA flows? So let's say you have multiple flows and 30% of them are default and 70% are NADA.
No, I mean, to be honest, this the parallel setting is the only one we tried a mixture meaning 1 versus 1. That's I guess that goes back to the question of a larger scale deployment. If we get to, let's say, configure, I guess the ideal case is that if we get to configure, different browsers running different traffic, then we'll get to look at the mix. That would be much more interesting. Yeah, but we don't have results on percentage-wise comparison. Yeah.
Okay. I think the percentage-wise comparison results would be helpful because they would actually help you see that if you have most of your web RTC traffic change into NADA, what can you expect your network to change into? So
I see.
Yeah.
So so okay. Thank you.
Thank you.
My guess is that Churching would be interested in collaborating if you wish to try this. Okay, thank you. I think that was a very interesting presentation. It seems to be pretty stable. It seems to compete pretty well with the other flows. So that seems to be pretty nice behavior. So thank you very much.
Thank you.
Are there any other questions? Okay, in which case I'll press the red button and see if you disappear. And nothing happens. No. Oh no, there we go. All right. God. Okay, so the only other thing we have on the agenda for today is a very brief update on the congestion control feedback draft from myself. So this is a draft which started out in this group. We had a design team in this group for quite a while, and then it moved over to AVT Core and has been developed there. And it's work that I've been doing along with Zahed, Varun, and Michael Ronaldo. The draft seems pretty stable, that the format hasn't changed for a reasonable length of time, and there's been only details for quite a while now. Since the last meeting, the only update has been to expand the design rationale section. We had an action item to explain how this relates to the other congestion control feedback mechanisms. So there were two changes. There was a small one to just add a mention of the receiver estimated maximum bit rate option. The draft already mentions the timber mechanism for signaling the feedback, and the RAMB seems to be a very similar mechanism. So I just added that in the same section to say it behaves broadly similarly, and there are details, but at the level of comparison we're looking at here, they don't make a whole lot of difference. And I also added a paragraph discussing the relation to the transport-wide congestion control extensions in the Holmer draft. Now, what that draft does is it adds an RTP header extension to each packet to give a single consistent sequence number across all the packets sent, and then reports feedback based on those sequence numbers. And that differs from the mechanism in this draft, which uses the existing sequence numbers in the packets and then reports per SSRC the loss for each sequence number. And the paragraph just explains that essentially the difference is that if you add this header extension, you get an extra 8 bytes per packet of overhead in that format, but it reduces the size of the feedback packets slightly. And if your goal is to do a rate calculation for the whole flow, then this simplifies the calculation because you're getting feedback for the flow as a whole. If your goal is to do rate calculations per SSRC, then obviously the format which reports per SSRC is simpler. So that's the fundamental trade-off here. It's trading off additional header overheads for simplicity if you're doing your aggregate level congestion control. We also note that the transport-wide feedback on a per SSRC basis is perhaps a more natural fit for RTP, since everything else in RTP is done per SSRC, whereas this aggregate feedback in the header extensions, it can clearly be made to work, but it fits less naturally into the framework. So we just added that description and made the usual set of updates to references, contact details, that sort of thing. Jonathan.
Yeah, Jonathan, thanks. I mean, I think the way I just expand on that last point about fitting more naturally is if we ever actually get to a point where we want to have multi-point congestion control, obviously having, not that anybody's working on that algorithmically, it's a really hard problem, but the CCFB feedback is much more natural because if you have multiple senders into the session, then obviously their sequence number, and they each have a transport-wide sequence number, though those sequence numbers will collide. Whereas if you're indexing them per SSRC, it just falls out naturally.
Yes. Per SSRC gives you more flexibility.
For topologies, yeah.
Yeah, or just in general, it gives you more flexibility because it makes it easy to treat each flow separately. If you want that flexibility, that's a win. If you're looking to treat the aggregate as a whole, then, well, you have to
maintain one map.
You have to map it back to a single sequence number space. Yeah. So that's basically all I had to say. As I say, we believe this draft is stable. It will be discussed in AVT Core on Friday. The presentation for me that I will give in AVT Core is identical to this one, except that this slide will say, please can we issue a last call? Anything else on this draft? Okay, that takes us to the end of the agenda. I don't know if anyone remote has anything they wish to bring up before we finish. If there's anything from anyone in the room who wishes to raise anything. No? Okay, in that case, we're done. Thank you, everybody.